Hi students, this is Mr. Bob, and in this video, we're going to talk about subtopic 7.1 radioactivity and subtopic 7.2 nuclear reactions. Before watching this video, you should hopefully have set up some focus notes on your own paper and have a colored pencil or highlighter ready. And again, you could also use a digital template if that works better for you. The other thing I wanted to say is I've listened to your feedback, and I think what might work best for you is that about 1 to 2 days after watching this video, at that point, you should go look at the sections in the book that I've outlined there below, if you have time. It's not absolutely essential, but it would be very much helpful to reinforce the concepts. And certainly what is important is for you to fill in, add, group, chunk, or highlight the notes and write in some questions where you have space, and also to identify any points of confusion. So number 2 is an absolute must. If you don't have time to look through the Giancoli sections, at least do number 2. Okay. And again, a couple more recommendations. I've already said these before, but just avoid that one mindless copying, okay? Please listen and pause the video as necessary. 2 essential questions for our video today. What factors impact the stability of the nucleus atom? And what is radioactivity, and what are the most common ways that radioactive decay happens? Okay, let's first talk about the unified atomic mass unit. So what this is basically, when we're talking about nuclear masses and nuclear reactions, we have to keep very precise track of the masses. And so we have established an atomic mass unit, or physicists did a long time ago. And we use the carbon-12 atom, the neutral version of it, as our standard. And we say that that's precisely 12 AMUs, atomic mass units. And so one atomic mass unit comes out to be 1.661 times 10⁻27 kilograms, which is also equivalent to a certain amount of energy. If you remember last class where we ended, we talked about the mass energy equivalence. This is in your data booklet, so there's no need to memorize this, but it's something you will have to use here. And so let's just talk about this quick example. How many atomic mass units is 25.32 grams of anything? Well, it's a simple unit conversion. What you would do is you'd set that up, okay? And then you know you're going from grams to kilograms, so that's going to cancel out there. And then you go from kilograms to atomic mass unit using the conversion that we just talked about. And you get your result 1.524 times 10 to the 25th U's. So I want to talk quickly about a little analogy just to make sure you realize how bizarrely different nuclear physics is in some ways. So if I'm at the store and I'm at the checkout counter and I have 3 pounds of apples in there, or let's say I'm just in the gross produce area and I measure 3 pounds of apples and I put them in my bag. What do you think should happen if I measure about another 3 pounds of apples and then put them in my bag too, so they're kind of all together, bunched close together? Well, 3 pounds here, 3 pounds here, you would think that when I put them together, if I put the bag on the scale, it would weigh about 6 pounds. Okay, let's keep that in mind as we proceed along here with nuclear physics. So let's do just a simple exercise here. We're going to compare the mass of a nucleus to that of its individual pieces and parts. Okay, so here you can see on the table on the right there, I have given you just reference masses, very elaborately, very precisely calculated in a lab for an electron, a proton, and a helium atom, a hydrogen atom, and a neutron. Okay, and these are in atomic mass units. So if we're going to use the information in that table, what value would we expect for the mass of the helium-4 nucleus? Okay, helium-4 nucleus. Remember last time we talked about this. Helium-4 means that it's got a mass number, or a nucleon number is 4. But we know helium from the periodic table has an atomic number of 2. So it's going to have 2 protons and 2 neutrons. So quite simply, we can just set up a table here. We got 2 protons. We got 2 neutrons. We know the mass of 1 proton from our table is given there in atomic mass units. Multiply that by 2, and we get a number there. And then we can do the same thing for the neutrons. And we get a number there. In fact, I would urge you to pause this video just to double check my numbers. Okay. And then when I add it up, I get a grand total that you can see is right there, a little over 4 atomic mass units. So one would expect if we measured the mass, precisely measured the mass of a helium-4 nucleus in a lab setting, that we would get this number, 4.031882 atomic mass units. Well, it turns out we don't. We do not get that number. We get this number over here. And notice these 2 numbers are not in agreement. And here is one point where I want to pause and just emphasize this idea. This is not because of some sort of lack of precision in the experiment. It's also not because we just need to basically more accurately measure the mass and eventually they would agree. okay? I'm going to tell you that for any nucleus, there's always going to be a difference. It's going to have less mass than what one would think it would have if we just add up all the pieces and parts separately. This is a fundamental idea of nuclear physics, a very important idea. And this difference that I just mentioned is what we call the mass defect of the nucleus. And so the mass defect is the difference between the mass of the nuclide and the sum of the mass of its individual constituents, okay? Very closely related to mass defect is this idea of binding energy. Remember Einstein's energy mass equation, change in energy equals change in mass times the speed of light squared. You can think of binding energy as the amount of energy that is required to split a nuclide into its constituents. So a key idea I want you to think about here is the following. Nuclei, when they come together, they have to give up some of their mass, and in giving up some of their mass, what they're doing is they're giving up some energy. And if one thinks about it, it has to be that way, because then what happens is you have a stable nucleus, one which would require some sort of energy input from an outside source in order to split apart the nucleons. If you think about it, if nucleons can just come together and not give up any of their mass, then they're going to be quite unstable, and they're going to be very readily, very easily just split apart. And in fact, so readily and easily that we really wouldn't have any sort of big structures like ourselves or anything you can think of, okay, in our universe. So this idea of mass defect is very pivotal to this understanding of the fact that the building blocks of all material, all matter that we can see, the mass defect has to be there. Otherwise, we wouldn't have matter in the way we think about it. And so you can also think of binding energy as the energy that the nucleus gave up when its nucleons became bound together. Okay, so these are two very important ideas that I want you to start thinking about and start sort of marinating in your mind, so to speak. So let's go ahead and determine the mass defect of the helium-4 nuclide. So I'm just going to take those two figures. The first one that I'm going to just copy down from the earlier slide, this was the mass of 2 protons and 2 neutrons. And then I'm going to subtract from that the mass of that helium-4 nuclide. And when I do that, I get this number here, 0.029279 AMU. So this would be the mass defect of helium-4. Okay, how do I get the binding energy? Well, this is very simply a conversion problem. I have atomic mass units, and we know already from the earlier slide that one atomic mass unit is equal to 931.5 mega electron volts of energy. By the way, if this is the first time you're seeing this unit, mega electron volts, just know it's the same idea as joules, just another unit. So when I multiply those two together on my trusty calculator, I get 27.27 mega electron volts. Okay, so two very important concepts. I would expect you to be able to, if I gave you, if I listed a nuclide and I gave you the mass of a proton and the mass of a neutron, I would expect you to be able to do something like what I just did here. Determine the mass defect and then determine the binding energy. Another way of looking at breaking apart and assembling the helium-4 nucleus is kind of this way. So if you look at this reaction, you have 2 protons plus 2 neutrons becoming the 4 helium nuclide, okay? Basically, the first scenario there, you can see it's actually disassembling the nucleus. And so disassembling the nucleus would take about that many joules of energy. And by the way, that's just basically the amount we got in mega electron volts converted to joules. So to take a helium-4 nucleus apart into its 2 protons, 2 neutrons, you have to give energy to that nucleus, which again is why it remains stable for long stretches. That's the binding energy. That's the energy, the lack of energy that keeps it bound together. And obviously the reverse process is the same idea, right? Like I just said, and when you get 2 protons and 2 neutrons coming together, they have to give up a little bit of their mass, and they do when they combine to become that helium-4 nucleus. So there will be a release of energy in that case. Okay, but an important idea that we use in nuclear physics is we look at the binding energy per nucleon of a nucleus. And really simply, all that is you take the binding energy of the nucleus and you divide it by the number of nucleons. So for example, what is the binding energy of the helium-4 nuclide? Well, all I would take is the binding energy of helium-4 and divide it by the number of nucleons in helium-4. And so let's just carry forward that result from last time, 27.27 mega electron volts divided by 4 nucleons. 27.27 divided by 4. We get that the binding energy per nucleon is somewhere around 6.82 mega electron volts per nucleon. Okay, and as you're going to see in a second here, this in some sense tells us the stability, gives us a measuring stick for the stability of a nucleus. Let's see how. Let's take a look at this graph and talk about a few things here. It's very important to realize what is being graphed here. And so on the right, on the y-axis, you can see it's basically graphed nucleons, or it's a graph of the nucleons, excuse me, the nuclides, I'm sorry, based on the number of nucleons in the nuclide. And on the vertical scale, it has plotted the binding energy per nucleon for those nuclides. Okay, so notice all the way out here on the right, you have one of the largest nuclides that exists, uranium-238. And so you can see there's a binding energy per nucleon for that. And over here is one of the smallest ones, right? We've already talked about deuterium. And you can see that there's a binding energy per nucleon for that nuclide as well, and all the ones in between. And so you get an interesting curve like this. Remember the helium-4 nucleus that we just talked about? That's right around here. By the way, there's a slight difference by what we calculated and what's on the graph. And that really has to relate to electrons. They included electrons in this scenario, and we didn't. Not a big deal. So what I want to say here is a couple things. The key ideas here you should realize is that there's this really stable the highest binding energy per nucleon is right around iron 56, okay? After iron 56, it begins to decrease, and before iron 56, it's also lower. And that has significant implications for what we observe in nature, which we'll talk about in the coming days and weeks. So 2 key ideas from this graph that I want you to think about. The key idea number 1 is, as the binding energy per nucleon of a nucleus increases, that means it's more stable. So just by looking at this graph, the most stable nucleus is this most stable nuclide is that of iron 56. Okay, it has the highest binding energy per nucleon, which means you would have to give it more energy per nucleon than any other nuclide on this chart to basically disassemble it. Okay, one of the least stable you can see there is basically deuterium, because you can see its binding energy per nucleon is really low. The second key idea is that in a nuclear reaction where energy is released, the binding energy per nucleon of the products is greater than that of the reactants. Okay, let me just say that again. This is a really important concept. This actually shows up a fair amount in IB examinations. If you have a nuclear reaction where energy is released, if you think about it, then the binding energy per nucleon of the products has to be greater than it was for the reactants. And that's what caused the energy to be released, right? Because when you formed those new nuclei, more energy was released than when you disassembled the previous nuclei. Does that make sense? Okay, keep those ideas in mind. So the other thing we can do is we can just do something like this. Using the graph, estimate the total binding energy of uranium-238. How would you do a problem like this? This is quite simple. All you do is you come across here and you estimate what this is. I would say that looks to be like 7.6. So binding energy per nucleon is roughly 7.6 mega electron volts per nucleon. But notice I'm asking for the total binding energy. So the total binding energy is going to be equal to 7.6 mega electron volts per nucleon times the number of nucleons, which we know for uranium is 238. It's given to us. So 7.6 times 238, we can roughly say that the total binding energy is this is an approximation for uranium-238 is roughly 1,800. I'm going to round to 2 significant figures, mega electron volts in this case. Okay, All right, let's talk about radioactive decay. And let's go back in history. Early 1900s, or late 1800s, excuse me, a dynamic duo, husband and wife, Pierre and Marie Curie, are working in Paris, and they announced the discovery of two radioactive elements, radium and polonium. By the way, Marie Curie, an amazing figure in science. Hopefully we'll get a chance to talk more about her later in the year, read up a little bit more about her. But you should do some research on your own if you ever get a chance, because she is amazing. So when they announced these elements that were radioactive, radioactive wasn't really a word that was in the jargon of science or anyone at the time. What does that mean? Okay, what it meant was the following, that when these elements were placed close to a radio receiver, like your common radio of the day, that receiver picked up some sort of interference that was coming from particles. There was some sort of activity associated with those nuclei that was causing some interference with the receiver. Okay, so out of this, the idea, after some further testing and exploration, the idea was realized that what's happening is there are these particles, these energetic particles leaving these nuclei. And that's what these particles are interacting with the radio receiver and causing that sort of problem that they were finding. So radioactivity is the spontaneous emission of energetic particles from the nuclei of certain atoms. And so the interesting thing is that studies showed this radioactivity was spontaneous and it was not affected by any sort of physical or chemical processes. And this comes back to what we were saying. Remember, chemistry has all to do with the electrons that are orbiting the nucleus. But stuff in the nucleus isn't affected by changes to the electrons that are orbiting it. So this was really interesting about this, is that this process wasn't affected by any of those normal chemical processes. Okay, so after further research, and this was many other physicists, not just Pierre and Marie Curie, but the discovery was made that there were three main types of radioactive decay that was occurring. And so we're going to talk about each of them, alpha, beta, and gamma. So if a radioactive substance's emitted particles pass through a magnetic field, this is what they did. They basically put a radioactive substance, they put it in a little chamber there, and then they would observe what happened as they exited those particles, and they sent them through a magnetic field. By the way, those X's you see there, that is a magnetic field, and we'll talk more about that in a later unit, actually. And so they discovered that sometimes these radioactive particles, when they went through that magnetic field, they deflected upwards, okay? Just a little bit. Sometimes they didn't deflect at all. And in other cases, these radioactive particles deflected downwards in the opposite direction as they passed through the magnetic field, okay? Well, the ones that deflected upwards slightly in this scenario, those are what we call alpha particles. And they consist of 2 protons and 2 neutrons. Basically, it's identical to a helium-4 nucleus. That's what it is, but you'll often hear it called an alpha particle. The ones that didn't deflect at all, those are what we call gamma rays, okay? And gamma rays, the fancy word we use for that in science is photons. You want to think of photons as packets of energy. You can also think of them as electromagnetic waves, okay? Electromagnetic waves, gamma rays are a type of electromagnetic wave, and they have no charge. And then finally, the third one, the one that deflected downwards, those are called beta particles, and that's just a fancy way of saying an electron, or if we're talking about the electron's twin evil cousin, if you want to call it, the positron, okay? Positron is the same thing as an electron, but it's just got the opposite charge, okay? So we're going to talk about each of these. My expectation is that you will be able to understand and talk about these 3 types of decay and write what we are calling decay equations, which you're going to see here. Let's first talk about alpha decay. When a nucleus emits an alpha particle, it loses 2 protons and 2 neutrons. Watch what happens here. Watch the image. Whoa, let's go back one more time just to make sure you saw that. Notice not only did that alpha particle leave, but notice we have a new element that stays behind. Okay, so the general form of this equation looks as follows. So what I want to make sure you understand here is that, remember, we talked about this last class, the normal sort of way we write nuclides is we write the symbol, the chemical symbol, then we write the nucleon number up high, and then we write the proton number down low in the lower left. So the general form of alpha decay is if I start with a nucleus or a nuclide that looks like this, then what I get is I get a new element which has a nucleon number that's 4 less than what I started with. And on the bottom here, this would be Z minus 2 because we know helium has two protons. One thing I'm not mentioning explicitly here, but you should know, is that there's the conservation of nucleon number and conservation of charge. And those are things that govern these equations. So in other words, I have to have the same number of nucleons up here at the top on the left as I do on the right. So this A has to be equal to A minus 4 plus 4. And it does. The same thing on the bottom, charge, if we want to talk about it this way, because protons are charged, Z has to be equal to what's here on the right, Z minus 2 plus 2. And it does. Okay, so notice what we have here is, here's an example that I just mentioned and that we just talked about, americium-241, okay? That becomes neptunium-237, and you get the alpha particle being emitted. And by the way, those are the Z numbers, so to speak, the proton numbers. Important thing to know is that alpha particles consistently have an energy of about 5 megaelectron volts. And that's really energetic. In fact, if you think about it, about 10 electron volts of energy is needed to knock electrons off atoms. That's a fancy word, or the fancy science word for saying that is ionization. So if you think about it, this means that at 5 megaelectron volts, one alpha particle can ionize a lot of atoms. It can knock off a lot of electrons. All right, beta decay, we have two kinds, beta minus and beta positive, beta plus, okay? In beta minus decay, what we have, the neutron becomes a proton in the nucleus. And in doing so, it ejects an electron and something else called an antineutrino. I should write that up here, and an antineutrino. Okay. So notice what happened here. Let me just make sure you see this. That orange proton, okay, or that orange neutron, excuse me, on the bottom here, becomes a proton. And in doing so, two things are emitted from the nucleus. So the general form looks like this. If we have X, and we start out with Z, then the nucleon number stays the same, okay? By the way, the electron does not have a nucleon, has a nucleon number of 0. And so what happens here, that, by the way, the antineutrino has no charge and a nucleon number of 0. So in other words, notice everything is balanced here. Excuse me, this is not right. This is Z plus 1 up here, okay? Because notice Z plus 1 minus 1 has to equal Z. Okay, so we have carbon 14, right? Which is 6 on the bottom here. This is 7, 0, 0, 0. This is an example. This is the example from the right. Okay, and on the bottom here, so this is beta minus. Beta plus decay, what we have is a proton becomes a neutron. And in this case, you get a positron, which is like the electron's twin cousin, except for it's got an opposite charge. Okay, and so this actually is wrong. This is Z minus 1, and this is A, 0, 0. So notice what I get here is I get a neutrino and a positron coming out. Okay. So alpha decay, beta decay, those are the two types. Third type that we're going to talk about here, actually after we talk about one more thing about beta decay. Just so you know, in contrast to the alpha particle, it was discovered that the beta particle could have a large variety of kinetic energies. So this was back in the 30s, and there was kind of a puzzlement about this. Well, people realized, well, if it has a large variety of kinetic energies, and if energy is not being conserved with the particles that we can see being emitted, then it must mean there's a particle out there carrying away some of the energy that we don't have a way of identifying, of detecting yet. Okay, and oftentimes in physics, math leads the way. So the math wasn't working out. It looked like conservation of energy was being violated. And so it took a while, but physicists eventually realized that yes, there is another particle, and it's called, and that's where it got the name neutrino or antineutrino. And it's an Italian physicist, Enrico Fermi, who coined this term because he said it's got to have no charge and it's got to be a lot smaller than a neutron. So we're going to call it a neutrino. Okay. So, and that's exactly what happened. This was discovered, I believe, in the 30s. So as you can see there, the neutrino carries away that extra kinetic energy. The beta positive decay produces neutrinos, the beta minus decay produces antineutrinos. And this will make more sense. Why is it neutrino, antineutrino? Why does one go with the other? This will make a lot more sense after we study particle physics later this year. Okay, last one, gamma decay. If you recall, electrons in an atom, if the electrons are in an excited state, they can basically move down to a lower energy level, and in doing so, they release a packet of energy. Again, formal scientific word that we call as a photon or light. Nuclei can also have excited states, and when a nucleus de-excites, it also releases a photon, and this process is called gamma decay. So there's the general form there, and this one's very straightforward. By the way, this star here, this means excited. Woohoo! Okay, so that is a nucleus that's excited, and it basically decays or de-excites, so to speak, and in de-exciting, it shoots out a gamma particle. Okay, notice it's excited, it's blinking, and then it shoots out that gamma ray, and it's no longer excited. So notice, here's one example, plutonium-234, okay, which I believe plutonium-234, I forgot off the top of my head, it's either 93 or 94 is the atomic number. Anyway, whichever number you would put down there. So this one's one of the more straightforward ones you can see, not much to it, but very important, we'll talk about it later. Okay, so that's it. Hopefully you now can talk about the factors that impact the stability of the nucleus of an atom, and you can talk about what radioactivity is and what are the most common ways that radioactive decay happens. Thanks.